Today's industrial chemistry would not be possible without catalysts. They speed up and steer the chemical reactions that yield the materials for stuff like sports shoes, clothes, and household appliances, to name a few. But for the sake of the planet, materials need to be produced with a reduced ecological footprint, so catalysts need to be improved. They must result in chemicals with higher purity, less waste, and fewer emissions. They might even make it possible to manufacture materials that are currently too expensive for the mass consumer market. That is why ARC-CBBC scientists conduct research into the synthesis of so-called heterogeneous metallic catalysts, which consist of metal particles embedded in a porous medium. The reactants and products flow through this. Preparing a new type of heterogeneous catalyst is a bit like cooking. It involves the laboratory equivalents of washing, mixing, dissolving, soaking and baking, and a lot of experimentation too. The important ingredient in most recipes are tiny particles of metal, measured in nanometers. The researcher's goal is to control the shape, size and location of these metal nanoparticles using conventional preparation techniques. But also unconventional ways to make catalysts are investigated. Perhaps the most innovative of these is to let the catalyst assemble itself. This can be done if the nanoparticles are confined in tiny droplets within a liquid that gradually evaporates. The residue consists of neatly packed nanoparticles ready for testing. To see what they've cooked up, researchers routinely use electron microscopes with nanometer resolution to image the nanoparticles. But often, they need to zoom in further into matter, to the level of individual atoms. This can be done using atom probe tomography. The catalyst material is shaped into an extremely fine needle, which is put under extremely high voltage. The outermost atoms of the needle ionize and fly off to strike a sensor that records the position and time of impact. On the basis of those data, a three-dimensional atom-by-atom image of the needle can be reconstructed. Unfortunately, such outrageously high magnifications can only be achieved in laboratory settings. To follow reactions under realistic operating conditions like those found in a chemical reactor, an X-ray photoelectron spectrometer is used. The catalyst sample is illuminated with X-rays. The X-rays kick out electrons from the surface atoms, and these electrons' energy can then be measured. From this, the composition of the catalyst and the strength of its atomic bonds can be deduced. But no matter what techniques are used for making and examining samples, the success of a new catalyst recipe is proved not in the lab, but in the performance of an industrial-scale chemical plant. How much more of the desired product and how much less of the unwanted byproducts does it yield? For a catalyst, this is the ultimate proof of success.